All in the new unit. In the previous unit, it was about the load flow study. This unit is about the short circuit studies. In our BTech classes, perform the short circuit study for the small system, and we know for the small system when it is 2 bus 3 bus system, then it is easy to solve by drawing the single line diagram, by finding the current, then finding the other parameter during the fault. But when the system is large enough, then we have to solve it with the help of either we have to form either Y bus or Z bus, and we have to find the voltage and currents of at all the nodes. But basic things in the first period, as basic things, we must know why the short circuit study or why fault analysis is required. What are the various types of faults, and what is the need of calculating the fault MVA or fault current. Normally, since as I told, power system is very big, complex, and it is subjected to lot of disturbances. Maybe disturbances may be of the type lightning may be there, heavy wind blowing may be there, heavy rain may be there, tree may fall on the transmission line, there may be colliding of vehicle with towers, there may be breakage in the pole, words may collide, line breakage may take. So in this way, there can be various types of short circuit or can be open circuit fault. But here let us have the first short circuit fault. Again, if the fault occurs in all the three phases, that is same in nature, means all the three wires, say they join to each other, then it will be the short circuit fault called the symmetrical fault. Such type of fault is called the symmetrical fault. It may happen that fault may occur in one line, it may happen in two lines, then it is not a symmetrical fault. Symmetrical fault means when the fault similar fault occurs in all the three lines, then the fault current or current flowing in each line will be the same, MVA will be the same. That's why that is called the and in those cases we need not to study the fault in the separate phases, but we can study the since all the phases are same in nature, similar in nature, so we can make the single line diagram and only one phase current can be calculated, and the same current will be in the other fault. So that type of fault analysis is done on the basis of the single line diagram, by drawing single line diagram and calculating the fault in one. And whatever the fault current is there in one, similar magnitude of the fault current will be there in others. But when it is a unsymmetrical fault, line to line or two line to ground fault, then we need to calculate it in a separate way. Now, anyway, once we are calculated, if we have calculated the fault current by multiplying the voltage, base voltage, we can find the fault MVA. Now, what is the need of this? Because fault current, uh, once we know the fault current, we can find out what type or what should be the rating of the circuit breaker. Because circuit breakers are those devices which has to open which will make the transmission line open by when the circuit breaker receive the signal from the signal when they receive the signal that the fault has occurred. So from the relays. So relay are those devices which actuate the circuit breaker by sensing the fault, and circuit breakers open. Now question is, during the fault, what is the current, what is the fault MVA will be there of the circuit breaker. So during normal condition, during normal condition, current flowing or power of the circuit breaker may be different, but during fault it may be different. It also depends when we want to depending upon the severity of the fault. When we want, whether sometime we want the fault should be cleared immediately within few milliseconds, within say 10 milliseconds. But sometime we can say, even if the fault occurs, we can no problem if the 200 milliseconds have been passed. 200 millisecond means 10. If 10 cycle have been passed, then up to that time we can hold the fault current, then it will not cause much problem. So depending upon what is our requirement, sometime we can require that it should be opened within 10 milliseconds. Sometime we can say, okay, let it be allowed for 200 milliseconds. And as soon as we want, depending upon the requirement, it will be the cost effective. We want the immediate interruption of the fault, then accordingly circuit breaker rating should be there. If we want, depending upon where it has happened, what is the severity, then the accordingly the rating and the price of the circuit breaker will be there. So this is the reason. So why we calculate the fault current and what is the use of the fault current. So now this is the background. Now, how to calculate the fault current? First of all, means fault current. As I told, during the fault, if it is a balance fault, balance means all the faces, face A, B, C, they have been joined to each other, and then it became earth or may not earth. So the current in each phase will be the same. That's why we do it on per phase basis. So first of all, we draw the single line diagram. So first of all, we draw the single line diagram of whole the system. Let it be, for example, although it may be different, but for example, I am saying it is a such type of single line diagram where is one source. It is a reactance of this source, reactance of the machine, XM. Reactance of this source machine. This is the reactance of the line. Reactance of the line, resistance of the line, and fault occurs here. It is the simplest possible circuit where it has been shown a short circuit transmission line fed by a voltage source. Now, let it be the RMS value of this voltage source. It is RMS value is say RMS value of this will be the if it is a generator, so RMS value of it, this will be the, we know, in case of a generator, RMS value is the 4.44 F 5 K and omega. This, do you remember that what is the RMS value? If it is simply a generator, then RMS value will be the 4.4 F 5 K omega. K winding factor and number of turns, 5 flux flowing into the generator, F is the frequency. So this is the RMS value of the voltage coming out. RMS voltage multiplied by under root 2, it is the maximum value of the voltage here. So means amplitude of the voltage. So this amplitude of the voltage and sin omega t is the signal. So this is the total net called the instantaneous value. At every instant of time, we have this type of voltage. E is equal to this given by under root 2 4.44 F 5 K omega sin omega t. This RMS of the voltage, let it be, it can be written as a V. So then it will be the E is equal to under root 2 V sin omega t. Means this can be written as a under root 2 V sin omega t. And now here, when the fault occurs, there will be, first of all, we will say what is the RMS value of the current. There are two types of current. One is the steady state current, another is the transient current. And even the steady state current, for calculating the steady state current, since this is a sinusoidal signal, voltage is sinusoidal, current will also be the sinusoidal signal. If it is equal to say Vm sin omega t, current will also be the Im sin omega t divided by the reactance. But the RMS value of this voltage is this under root 2 V. So then current, RMS value to current will be under root 2 V divided by this. This means R plus JXL plus XM. Both reactance, line reactance and machine reactance. R plus JXL plus XM. So means RMS value of the current will be the V under root 2. This is a V, so under root 2 V divided by R plus JXL plus XM. ये हमारी आरएमएस वैल्यू ऑफ द करंट हो गई। ना व्हाट इज द साइनोसोडल वैल्यू ऑफ द करंट, जैसे ये हमारी आरएमएस वैल्यू, उसमें √2 का मल्टीप्लाई करेंगे तो एम्पलीट्यूड और साइन ओमेगा टी, तो उसमें भी साइन ओमेगा टी। नाउ डिपेंडिंग अपॉन द पावर फैक्टर ऑफ दिस, उसका पावर फैक्टर जितना इसका पावर फैक्टर होगा वो उसका पावर फैक्टर इससे उतना कम, ये द पावर फैक्टर ऑफ दिस इज 0, तो पावर फैक्टर ऑफ करंट विल बी गिवन बाय sin omega 0 minus this means omega, so power factor means phi, sin phi will be there. So let us see what is the current. This E is equal to √2V sin omega t, our voltage source. This is the impedance. There are two type of currents as I told, steady state current, transient current. Steady state current will be √2V by Z. Z क्या है ये R plus JX. So voltage is sin omega t, current will also be sin omega t with some power factor angle. Power factor angle theta is given by tan inverse x, ये है tan inverse x by r. Tan inverse x by r, depending upon the value of x and r, the power factor angle will be there. So this is the sin omega t minus theta or phi. This is the steady state current. I hope you might be knowing this is the steady state current, and we know in addition to this in the circuit there is a tangent current too. Steady state current भी होता है circuit में, and there is a tangent current. Tangent current क्या होता है? You know, is anybody you know why there is tangent current? Even if there is no source and if we give a pulse, then there will be some current flowing into this, and this current will be e to the power minus t L by R. इसमें जैसे ही एक पल्स देंगे इसमें एक करंट फ्लो होगी और e to the power minus t L by R. L means total inductance divided by R. तो ये डिके हो जाए, e to the power minus t L by R means when t is equal to infinite, current will be 0. In the beginning, current will be high at t e to the power minus, when t is equal to 0, e to the power minus t L by R. So when t is 0, e to the power 0 is equal to 1, तो उतना maximum current होगा, and finally it will decay, means current maximum, and then it will be decaying like this. So this is the tangent current, and this tangent current is there because of the initial pulse given. Initial pulse, or may not be, even if this voltage source, when you make this switch into the, when this source into the circuit, then immediately a pulse will be applied and both steady state and tangent current will flow. So this is the equation for tangent current, e to the power minus t, e to the power minus t, it is a t divided by L by R. Okay, so total current will be this e to the power minus e to the power minus t L by R is the tangent current, and √2 by Z is sin omega t minus theta is the steady state current. So steady state sinusoidal current. So both the currents are there in the system, and now to know what is this A constant. To know this A constant, we apply a condition that at t is equal to 0, current is 0. देखिए, we in the load flow study, in the short circuit study, we assume that load current is 0. Load current is normal, although load current is not 0. What is the load current in any circuit? कोई भी नेटवर्क है उसमें लोड करंट क्या होगा, कैसे पता लगाएंगे? लोड करंट can be calculated with the help of the load flow study. If you perform the load flow study, we can know what is the load flowing, what is the current flowing in each component. But here we assume the load current equal to 0, because since we are going to study the short circuit study means fault current is very high in comparison to the normal current. Normal load current, say if it is a 10 ampere, then fault current may be 150 ampere during fault, during steady state, during the when it has occurred, fault has occurred. So fault current is 10 to 15 times. So in comparison to 10 to 15 times, load current is considered as equal to 0. Otherwise, load current is not 0. In comparison to the fault current, it is compared to be 0. Otherwise, it is not. So we assumed in the beginning, load current is 0. Line is unloaded while the fault has occurred. So here when we apply a t is equal to 0, it is 1 and it is 0. So this A will be equal to this √2V by Z sin omega t minus theta. So and t is equal to 0, this is equal to 0 √2V by Z sin theta, and that becomes the like this. So this is A. Put A here. So actual current is this. देखिए, now what we expect, जैसे ही फॉल्ट होगा हम क्या कहते हैं, आरएमएस वैल्यू 220 है, तो हम सोचेंगे 220 डिवाइड बाय द इम्पीडेंस, इतनी करंट होना चाहिए. बट for the fault analysis अगर हम आप देखें शॉक जो लगेगा या जो हमें इक्विपमेंट चाहिए प्रोटेक्शन के लिए कितने वोल्टेज के लिए करिए अंडर रूट नॉट वी वाई जेड करंट के लिए इक्विपमेंट प्रोटेक्शन नहीं करना है, हमें चाहिए वी वाई जेड बिकॉज करंट इज फ्लोइंग टू द मैक्सिमम, ये आरएमएस वैल्यू है, लेकिन उसमें प्रोटेक्शन तो हमें मैक्सिमम से चाहिए ना, जैसे साइनोसॉइडल है प्रोटेक्शन चाहिए इवन इफ ये आरएमएस वैल्यू इज द डिफरेंट, आरएमएस वैल्यू मैक्सिमम से डिवाइड बाई अंडर रूट 2 होता है, बट ये इसका पीक से भी तो प्रोटेक्शन चाहिए, जो equipment should be protected from the peak current also, so that is the under root 2 v of z, RMS and root 2 v, and we know not only that but tangent current is also flowing, this is also again same equal to under root 2 v by z, so there can be a maximum to maximum current may be this plus this under root 2 v by z and under root 2 by z, so it is 2 into 2 by under root 2 it is 1.4 and 1.4 multiplied by 2 it will be 2.88, so it nearly you can say it is a 3. If v by z is equal to, say for example in v by z is equal to we are saying in terms of ampere 10 ampere, then we have to protect not with the fault current is say v by z is 100 ampere, we have not to protect the equipment for 100 ampere, but we have to protect the equipment for 300 ampere, that's why the fault current is very necessary to be calculated. From here we have seen. Now if we plot this, this is steady state means when t is equal to infinite, or after infinite means after say 10 cycle 200 millisecond, after 10 cycle you see this current is the steady state current, this RMS value of this is the steady state current, peak under root 2 by z, peak is this, from here to here it is under root 2 by z, but in the beginning not only this current is also flowing, this current is also equal to nearly this current, so this is nearly 2 times of that, and this sum of this and this will be equal to RMS 3 times of RMS value, ये इससे हमें इसको सिस्टम को प्रोटेक्ट करना है. Now we will see not only we have to protect for the 3 times of the RMS value of the current, we have not only to protect the system for 2.8 or 3 times of the RMS value of the current, fault current, but we have to protect the system more than that. Why? Here so far, now देखिए, so far we have assumed, if you see this figure, we have assumed the reactance of this generator is fixed, but in fact the reactance of this generator is also not fixed. Reactance of the generator is also not fixed. We know now what is the reactance into the synchronous generator. Reactance in the synchronous generator is the leakage reactance. We know in the synchronous generator there is a leakage reactance, there is a armature reactance, there is a damping winding also. If you see the winding of the synchronous machine, synchronous generator, there is a damper winding also, there is a field winding also, there is damping winding, there is a field winding, and armature is the reflect of the main winding current. मेन वाइंडिंग में जो करंट जा रहा है उसका फील्ड को अपोज कर रहा है, दैट इज द आर्मेचर रिएक्शन, एंड अदर देन दैट देयर इज लीकेज रिएक्टेंस विद द फ्लक्स इज बीइंग लीक्ड, so because of the leakage of the flux there is a leakage reactance. So net reactance, if you remember the configuration of the synchronous generator, then net reactance of the synchronous generator is given by XL, this XL leakage reactance plus armature reactance, field reactance, and damper winding reactance in parallel. This is the net reactance of the system. So, and what actually happening? What is the purpose of the damper winding? Just to, although you must be knowing, but just to understand what is the purpose of damper winding and where it is put. If you remember the shape of the synchronous generator, then you know in the armature there is armature winding. Damper winding is on the front of the rotor, and they are short circuit on both the side. जैसे इंडक्शन मशीन की वाइंडिंग होती है, सिंक्रोनस वाइंडिंग देखिए, इन केस ऑफ सिंक्रोनस जनरेटर द वाइंडिंग ऑन रोटर एंड वाइंडिंग ऑन द स्टेटर इज ऑफ सेम टाइप. जो हमारा स्टेटर में वाइंडिंग फील्ड वाइंडिंग, the field winding is different, and armature winding is Field winding may be say on the rotor, then armature winding may be on the stator. But in addition to that, on the rotor, in addition to the field winding, there are few slots where it is short circuited, where the both on both the side of the rotor they are short circuited. That winding is same as of the induction motor winding. And whenever the disturb, देखिए, in case of synchronous generator, we know it is running at a constant speed. When speed is or at a synchronous speed, when it is running at the synchronous speed, then there is no change of flux between the field winding and winding on the rotor, because both are on the same. Field winding और rotor की winding साथ साथ, field winding, and but when it is not a synchronous speed, then at that time, means during disturbance, what will happen? During disturbance, the speed will not be equal to the synchronous speed. At that time, their damper winding will behave as a induction motor, and because of rate of change of flux, it oppose by which it is produced. तो वो उस disturbance को oppose करता है. That's why anyway, that is about the synchronous generator or induction motor theory. But we know the damper winding is there. It is the field winding, that is the armature winding, and when it has after some time, when disturbance has gone, then damper winding will not have any effect. That will be removed from the circuit. But in the beginning, all armature, field and damper, all winding plus leakage reactance, this is there. So since they are in parallel, so net reactance is less. When net reactance is called the subtransient reactance, which is denoted by XD double dash. But after some time, depending upon the टाइम कांस्टेंट, ये रिएक्टेंस है ना, XDW मींस रिएक्ट L, इसमें इसका रिएक्टेंस भी है, इसमें कुछ रेजिस्टेंस भी होगा, तो X E / T L by R डिपेंडिंग अपॉन द वैल्यू ऑफ L एंड R ऑफ दिस, ये डिके हो जाएगा, मींस उसका जो L by R जो करंट था, ट्रांजिएंट करंट, वो उस पोर्शन के लिए डिके हो गया, इसका इफेक्ट खत्म हो गया. आफ्टर सम टाइम इसका पावर, इसका डिकेइंग L और R की वैल्यू के अकॉर्डिंगली it will be decaying. So in the beginning, all reactance is there, that is called the subtransient reactance. After that, damper has removed, it become the transient reactant. When armature has also been out of circuit, then only XL plus XA will remain. That is called the steady state current. So we know when we said above, XM is the machine reactance. Machine reactance that we have represented as a steady state reactance. When we said XM, and XM was nothing but it is a steady state reactance, and that was equal to XL plus XA. But in fact, in the beginning, reactance is less than that. So when in the beginning reactance is less than that, so current will be XM is less. So Vy जो था ना, Vy XM, Vy Z is less now. So total current will be not in the steady state only. Okay, when in the steady state, when reactance is equal to XM is equal to XL plus XA, then okay, this current is there, which we have described above. This portion we are describing by this. But in fact, by considering XM as a constant value, but in fact, XM is not constant, and this will, in addition to this current is there, subtransient current and transient current. And this subtransient current is, again, this can be nearly equal to this. And we know that this is not only the RMS current, it is this was the 3 times of the RMS current, this value. And this again 3. So 3 to 3 means 6 times. 5 to 6 times of the RMS current. तो हम सिंपली ये ना सोचें कि वोल्टेज बाई जेड सिंपली 220 बाई इम्पीडेंस डिवाइड करके हम देख लेंगे कि ये फॉल्ट करंट है. तो फॉल्ट करंट कैन बी एज हाई एज 5 to 6 times of the RMS value of the current, for which we have to protect all the devices. So that's why to study the fault current is very much required. Now how to, तो इसका मतलब क्या हुआ, हम when we calculate the fault current, first of all is, once we calculate the fault current, now we have to see actual fault current will be, we have to calculate the RMS value of the fault current. Then we have to see what will be the actual fault current, what will be the fault current in the equipment. And depending upon the requirement, if we consider immediate effect, then we have to multiply by multiplying factor this. Then after 7-8 cycle, we can say there is no multiplying factor is there, because that effect has been may be removed. So here you see, this we take. If we consider immediate after 2 cycle, its effect can be 1.4 times of the multiplying factor. It is there. DC, it is the DC offset current. Transient जो current था, DC offset current. Its effect will be after 8 cycle. Its effect will be 0. Transient current will be removed. So we can say, we can multiplying by, to see the DC offset effect, we can multiply this multiplying factor into the RMS value of the current. और फिर उसमें अंडर रूट का मल्टीप्लाई करेंगे, उसका मैक्सिमम वैल्यू, और फिर इसमें ट्वाइस कर देंगे, तो ये वाला इफेक्ट ऑफ tangent and subtangent will come. So first of all, we have to, now it is not what effect is to be taken, but now we have to, first of all, we will see how to calculate the RMS value of the fault current. This is one, and then we will see what multiplying factor is to be applied. That is the secondary thing. So first of all, we have how to calculate the fault current. This we are now going to study. So first of all, what we do, in, as I told in the beginning also, during the fault analysis, first of all, we draw the single line diagram. सबसे पहले तो single line diagram draw करते हैं. We convert all the system into the per unit system. Now, then we, first of all, here you see in this balance fault or small system, in the balance fault and the small system, we convert the whole network across the fault. Across the fault means जिस बस पे fault है उसके across, just to see from that bus, we convert the whole network into the Thevenin's equivalent. सपोज करिए बस नंबर 4 पे हमारा फॉल्ट आ गया, तो एट बस नंबर 4, फोर्थ बस को से देखते हुए हम थेवेनिन्स इक्विवेलेंट बनाएंगे, और थेवेनिन्स इक्विवेलेंट में वी विल ऑब्टेन द थेवेनिन्स इंपीडेंस एंड थेवेनिन्स वोल्टेज, एंड व्हाट इज, एंड वी नो, तो वी मस्ट नो व्हाट इज द थेवेनिन्स थ्योरम. We know Thevenin theorem is that it states that any linear network containing any number of voltage sources, because number of sources may be there, number of generator may be there, number of impedances may be there. So any network containing any number of voltage, any impedances can be replaced by a single EMF and then single impedance in series, where EMF is an open circuit voltage across the terminal, across the fault terminals, and the impedance is the impedance seen from those terminals, keeping all voltage sources short circuited. तो ये मतलब क्या हुआ, थेवेनिन्स इक्विवेलेंट बनाने के लिए कैसे बनाते हैं ये बता रहे हैं. थेवेनिन्स इक्विवेलेंट बनाने के लिए जितनी इम्पीडेंसेस हैं उसको उस सीन फ्रॉम दैट साइड कितना इम्पीडेंस आ रहा है, और जब हम थेवेनिन्स इम्पीडेंस बनाएंगे तो वोल्टेज सोर्स को शॉर्ट सर्किट कर देंगे. ओके, नाउ फिर क्या करेंगे, सिंगल लाइन डायग्राम प्लॉट कर लेंगे पर यूनिट के लिए, और पर यूनिट कन्वर्ट कर लेंगे. रेजिस्टेंसेस को नेग्लेक्ट करते हैं शॉर्ट सर्किट स्टडीज में. रेजिस्टेंसेस आर नॉट मच इंपोर्टेंट, दोज आर नेग्लेक्टेड बिकॉज रेजिस्टेंस इन कंपैरिजन टू इम्पीडेंसेस आर स्मॉल. तो एंड देन वंस वी नो थेवेनिन्स वोल्टेज, थेवेनिन्स करंट, Thevenin voltage, Thevenin impedance, then fault current will be simply, fault current is the Thevenin's voltage, Thevenin's impedance plus the impedance by which the fault has occurred. Suppose बस नंबर 4 पे एक तार के थ्रू शॉर्ट सर्किट हो गया, तो उस तार का impedance प्लस Thevenin's impedance, ये नेट impedance हो गया, ऊपर Thevenin's voltage, ये fault current आ गया. fault current में हम मल्टीप्लाई कर देंगे बेस वोल्टेज का, तो क्या आ जाएगा, फॉल्ट एमवीए आ जाएगा. वही फॉल्ट एमवीए हमारा किसका होगा, फॉल्ट एमवीए जो हमारी सर्किट ब्रेकर्स वगैरह है उसका फॉल्ट एमवीए होगा. सो दिस इज अबाउट फॉल्ट करंट, हाउ टू कैलकुलेट फॉल्ट करंट, देन हाउ टू इनकॉर्पोरेट or we can take it from the in the next class. Do you want to continue, or we should take it into the next class? Hello.
Sir,
So I think
better to discuss in next class, sir.
Sufficient time has been. We can take it into the next class, and up to now, if you want to discuss, you can discuss.